It's that time again. Time for some more definitions. An Euler path is a path that travels over every edge once and only once. An Euler path exists if exactly two vertices have a degree that is an odd number and the rest have a degree that is an even number. The Euler path will start at one of the vertices with an odd degree and end at the other vertex with an odd degree. An Euler path also exists if all vertices have a degree that is an even number, but this is a special case called an Euler circuit, which we'll talk about in a minute. Let's look at an example to see how this works out. We're shown a path here, and in this path, we've got a number of vertices and a number of edges connecting them all. If I take a look at the degree of each vertex, I can see that A is 4, B is 2, C is also 4, D is 3, and E is 3. If we consider the rule for an Euler path, we can see that we have two vertices that have an odd degree, both of them have 3, and the rest are even. That tells us that it's possible to have an Euler path. We also know that when we're going to draw the Euler path, we have to start at one of those odd-numbered vertices. So we look at E and D as our starting points, and I'll go ahead and see how this maps out. We want to cover every edge once without repeating. We are, however, allowed to repeat vertices, so we've completed our path. And we record the path as ECB, ACD, AED. An Euler circuit is a circuit that travels over every edge once and only once. It's an Euler path that starts and ends at the same vertex. An Euler circuit is a special case of an Euler path, as it is an Euler path that begins and ends at the same vertex. An Euler circuit exists if all vertices have degrees that are even numbers. Let's take a look at an example. Find an Euler circuit in the example below. We start off by identifying the degrees of each of the vertices. So looking at A, we see it's got a degree of 4, B is a degree of 2, C is a degree of 4 as well, D is a degree of 2, and E is a degree of 2. Now, we can see from this, it's the second case where every vertex has an even degree, so we know that we can find a Euler circuit in this graph. In fact, there are many. To start the Euler circuit, I'm going to begin at A, go to C, from C to B, B to A to E, E to C, C to D, and D back to A. So I know I've got an Euler circuit because I've covered every single edge exactly once, and I ended up back at the original vertex. Try this question. We're asked to find if an Euler path exists in the graph below, and if it does, to identify it. To determine whether an Euler path exists, first of all, we need to check the degree of every single vertex. Vertex A has a degree of 3. Vertex B has a degree of 4. Vertex C is 4. D is 2. E is 3. And F is 4 as well. Do a quick view. We can see that we've got two vertices that have a degree of 3, which are odd numbers. So we know that we can have an Euler path in this graph. Now we need to find the Euler path. To find an Euler path, we need to start at one of the vertices that has an odd number. In this case, I'm going to go from A to F, from F to E, from E to C, from C to B, B to F, F back to C, C back to A to D, D to B, and finally B back to the original vertex of E. So we've covered all of the edges, and we ended up actually back at the same vertex. So if we write out the Euler path, it's A, F, E, C, B, F, C, A, D, B, E. Let's look at the next graph and see if an Euler path exists for it. Same approach, we want to identify the degrees of each vertex. The degree of vertex A is 3. The degree of vertex B is also 3. The degree of vertex C is 2, D is 2, E is 2 as well, F is 3. As soon as I get to that point, I realize I've got 3 vertices that have an odd number. The rule is that for an Euler path, only 2 of the vertices can have an odd number. In this case, we've already gotten to 3 vertices with an odd number, so we know we're not going to have an Euler path. To complete it, just out of curiosity, the degree on G was 2, and the degree on H was also 3. So the answer here is that there is no Euler path. Now we're asked, does an Euler circuit exist in the graph below? And if so, to identify one. The first thing we want to do is figure out the degree of each of the vertices. Remember that if it doesn't meet the requirements of either having exactly 2 odd degree vertices or all even vertices, there won't be an Euler path. So that's our first step. So the degree of A is 2, B is 4, C is also 4, D is 2, E is 2, F is 2, and G is also 2. So in this case, it meets the second criteria where all of the vertices have an even number. Now we're asked to identify an Euler path. It's not as straightforward as when we have an odd number and we know where we're going to start and end. In this case, I'm going to choose to start at A, and I'm going to go to G, to C, down to D, to B, over to back to C, to F, to B, finally to E, and back to A. So we've met the criteria. We started and ended at the same vertex. We covered each edge exactly once. Same question with this graph. We can see very quickly that the degree of each vertex is the same. It's 2. We've got even degrees on all vertices, and it's not too hard to see that we can go A, D, D to B, to C, and back to A. We started and ended at the same vertex, and we covered all of the edges, so we do have an Euler circuit in this case. The definitions you need to remember from this lesson are Euler path and Euler circuit.